written in one dimension.
Yes.
Can we say that from the monodromy it will always be identical?
Well, in one dimension, the point is if you try to calculate the Riemann tensor, right, it is always 0 because it is antisymmetric, right? It's antisymmetric in the two indices. First two indices and the second two indices is antisymmetric, right? If there is only one index, then it cannot be 0, non-zero, right? So Riemann tensor is identically 0 in one dimension. Monodromy, of course, again is trivial because there is only one tangent direction, right? So you cannot change to anything else.
So can we approach the problem from that direction also? Since there is only one coordinate,
Yes.
you can vary it to go to one path and you will have to retrace that path back if you are trying to go constant.
Yeah, there is no concept of closed path which is not identically 0.
Yes, yes, yes.
Right, yeah. Okay. Except that you can of course go around. So it's a circle, for example. Okay. You can go around, but even then there is no chance of a monodromy because it's only there is only one tangent vector, right? So it cannot change its direction in any case. Any other questions?
If any case that we can parameterize in some kind of a one-dimensional space unorientedly, like we parameterize always think of the fact that a parameter goes from 0 to 2 pi and traces the manifold, right? But can we do it unorientedly? Because there is a orientation idea of orientation in parameterization.
Yeah.
But can we?
Well, you don't have to. Meaning you can also do the opposite.
But in principle, one can do it.
Yeah. Meaning
In that case, also like this statement is so trivial for monodromy, or is that?
Meaning one dimension, the point only non-trivial. This thing is you can either have a straight line or a circle.
Yes.
So there is not much
Options there.
option that you can have anywhere.
Yes, but what are
In higher dimension, you can this question makes sense. Right? So there is the manifold is orientable or not orientable.
Yes.
In one dimension, it's there is a notion of non-orientable manifold, for example, right?
But in case of two-dimension, non-orientable surfaces does exist.
Yeah. Any other questions? Okay. So let me write down the equations again. That will be using here. So rho square d phi dt is k psi. This is what gives you the time dependence of phi. And then the other equation I'll write in terms of the relation between phi and rho. So d phi d rho is k root phi over rho square 1 over n minus k square over rho square. And let me remind you that chi is or psi is 1 over chi. And this is 1 minus 2gm over rho. So last time we considered the motion of a photon, the trajectory of a photon, and for that we set n equal to 0. Today we will be considering motion of a massive particle. And as we have seen, for massive particle, n is negative. So these we will cover, for example, the motion of planets around the sun. So first we will try to examine qualitatively what kind of trajectories can we expect. In the standard central force problem, okay, or 1 over r potential in Newtonian gravity, we know that there can be bound trajectories and there can be unbound trajectories, right? Trajectories which revolve around the origin, around the center, and trajectories which represent objects coming from infinity and going up to infinity. So we will first try to classify what kind of orbits we can have in this case. So for that, we note that we will be focusing our attention to the region rho greater than 2gm. Later we will discuss what happens for rho less than 2gm. But at least for today's analysis, we will be focusing on at least the beginning of today's analysis we will be focusing on this region, rho larger than 2 GM. So in this region, psi and chi are positive. So we see from this equation that d phi dt is either always positive or always negative depending on whether k is positive or negative. Okay. So the phi cannot turn around. Okay. And we can always choose d phi dt to be positive, that means you can choose k to be positive. Okay, because negative k is exactly, you can change k to minus k by redefining phi, right? Just define phi as minus phi, the equation will look unchanged. So we will focus on the case where k is positive, so the d phi dt is positive. So we take k greater than 0, where d phi dt remains positive. So there is the qualitative information about the trajectory comes from rho versus phi, how rho changes as a function of phi. Okay, phi always increases, we know. So studying rho as a function of time qualitatively is the same as studying rho as a function of phi. Okay. So let's first see where d rho d phi can vanish. Or let me write this equation in a slightly different way. So here you have d phi d rho, but we see from here that it's probably more convenient to think of d rho d phi, because you want to see how the rho can, for example, d rho d phi can it change sign. So let's write d rho d phi as rho square over k root I. And let me also emphasize that here, this sign, when you take the square root, because there is a square root, you can either choose the positive sign or the negative sign. Okay? But the way d rho d phi can change sign is by this becoming 0. As long as this remains positive, d rho d phi cannot change sign. Okay? So rho will continue to increase with phi or decrease with phi. So d rho d phi has to reach 0 and then it can change sign. So it's clear that the important quantity to analyze, at least first to get the qualitative picture, is when this quantity is positive and when this quantity is negative. Because you know that this quantity, for example, cannot become negative, okay? Because then it doesn't make sense. Okay? So if this passes through a 0, that's the point where d rho d phi will have to change sign. Okay? Because rho cannot continue to decrease or increase anymore. Okay? Because that may drive this quantity to a negative. So that will force d rho d phi to change sign, and that's consistent because after all this is vanishing. So d rho d phi is 0 when this is 0. Now we can look at this, but we can also look at a slightly different.
So this says that for if we try to study the change of rho with respect to phi, then there will be a closest distance or maximum distance for every trajectory.
Well, not necessarily. We'll see what I mean.
If it goes to 0.
Yes, if it goes to 0, then of course rho it will turn.
Yes.
Right? But when the question is there a condition under which it goes to 0?
So how can d rho d phi be negative?
How can d rho d phi be? Because there is a square root,
Oh.
right? So you could pick a negative sign. Right? But to change from plus to minus, of course d rho d phi should be continuous, right? To change from plus to minus, it has to go through 0.
Yeah.
Right? So this has to become 0. Once this becomes 0, right, then d rho d phi could become negative. Is this okay? Okay, so let's try to do something slightly simpler, which is that let's take this root chi inside, because chi after all is one word psi, right? So taking the root chi inside means inside we will multiply by psi. So using chi equal to 1 over psi, we can write this as rho square over k times n minus a square over rho square times psi plus 1. Okay, and let's write this out explicitly. So this is n minus k square over rho square 1 minus 2gm over rho plus 1. And if we define x as 1 over rho, then this becomes n minus k square x square times 1 minus 2gm x plus 1. Okay. And the region under study is now is rho larger than 2gm. Let me write it 2gm and this means that x should lie between 0 and 2gm. Okay, this is a region of physical interest. Okay, we will be studying the behavior of this function in this region. So this function we will call f of x. You want to try to plot f versus x. So let's call this as 1 over 2gm. This is 0. Okay, so you want to study the function in this range. But even if you are interested in this range, it's useful to think of this function over the whole range of x. And the reason for this is that this is cubic in x. Right? So you know that a cubic function has at most 3 roots. Right? That there are at most 3 places where it can vanish. Okay? So it's useful to think of this as a function over the whole range, minus infinity to infinity, even though we will eventually be interested in knowing the behavior in this range. So let's try to identify some of the regions where we can easily study this function. First of all, for large x, right? X is large, then what happens? It goes to plus infinity, right? So that this goes as x cube, the x cube coefficient is positive. So it goes to plus infinity. So for large x, it's somewhere here. And for small x, or for large negative x, the same argument tells us that this function goes to minus infinity, right? 2gm k square x.
From the structure of the equation, we can readily figure out what the solutions will be.
We can?
Readily, since it is n minus k square x square.
Yes.
So that will means that will be factorized. That will easily factorize.
No. It is last one.
Oh, achha.
Right? Yeah. So this whole thing is the function. So it's meaning it's not easily. It's not straightforward to figure out what the properties are, because the result actually depends on n and k. Okay, what kind of function you will get does depend on n and k. Okay, and we will consider those cases. And we will see that All of them describe something physical. Okay. So you know we have identified these two x. Now, if x is 1 over 2 gm, then this becomes 0 and it's 1. Right? So the function is positive, it's 1 here. Okay, so there is one more point we know. Okay. In fact, we know something more, because if x is larger than 2 gm, sorry, if x is larger than 1 over 2 gm, then this is negative. Okay? And this one is also negative because n is negative. Okay? So if x is larger than 1 over 2 gm, then we know that it's a product of two negative numbers, which is positive plus 1. So the function remains positive. So between here and here, there is no possibility of getting any 0. Okay, it's positive. Now let's look at what happens at x equal to 0. At x equal to 0, the function is given by n plus 1. Because n plus 1. Now we know that n is negative, but we don't know whether n plus 1 is negative or positive. That n plus 1 could be negative or positive, so we'll be considering both cases separately. Okay, n plus 1 negative and n plus 1 positive. So this already distinguishes these two cases. So case 1 will be n plus 1 positive, and case 2 will be n plus 1 negative. So let's start with, but I have to do the other. Case 1 is negative, case 2 is positive. Okay, because I have to start with case 1. Okay, so let's start with case 1, n plus 1 negative. So it's here. So now we are considering case 1. Now we see that between these two, there is at least 1 0. Now there can be 1 0 or 3 zeros. It cannot be more than 3 zeros, right? We don't care about this region actually, because the point is we are only interested in, this is the physical region, right? So we don't care about what happens in this region. Between these two, there can be either 1 0 or 3 zeros.
But in principle, zeros can lie also over there.
Yes, zeros can lie on this side or on the complex plane. Right? So
At least 1 0.
yeah, at least 1 0 is clearly there. There can be 2 zeros. 1 A is 1 0. And case 1B will be 3 zeros. In which case, of course, there cannot be anything on this side.
So we can find for case 1b the maximum and minimum of the function values.
Yes, we can, but okay, let's just proceed. You just right now we are just studying qualitatively. Okay, what are the possibilities? So let's look at this possibility first, right? What kind of motion will it describe? So we see that first of all d rho d phi can vanish only here. Okay. Furthermore, this function, the physical region is when this function is positive, right? Negative region means that this thing under the square root is negative. So that certainly is not a physical region. So the physical region is only on this side. Okay. This is the 1 over 2 gm, right? We don't want to go beyond this, right? X larger than 1 over 2 gm means rho less than 2 gm. Okay. That we will study later. Right now we don't go there. So this is the physical region. So this basically means that there is at most one turning point. So there is at most one point in rho space where the motion can turn around. And eventually the fate of this motion will be that it will fall into the event horizon, the rho equal to 2 gm. Is this clear? Even without solving any equation, you can see what this, what kind of motion this will describe. Right? X equivalently rho, right, can dx d phi can change its sign only at one point, and after it has changed its sign and after it has started increasing, x has started increasing, there is nothing to turn it back. Okay, it basically crosses the x equal to 1 over 2 gm radius. Is this clear? Okay. So this will describe some kind of trajectory. Imagine that we are starting close to 1 over 2 gm. Okay. We throw the particle up with a small velocity. It will go up a little, turn around and go back. Okay. That's the kind of motion it can describe. Is this point clear?
Could you repeat this?
Yes. So let's look at this motion, right? So you have to just keep in mind that increasing x means decreasing rho. Okay. So d rho d phi can turn around only here. Okay. Phi always is increasing. Okay. So let's look at it as a function of phi, which is the same as a function of time. Okay. Suppose it was rho was increasing to begin with. Okay. Starting from somewhere here. Okay. Rho was increasing means x was decreasing. Okay. It reaches here. Okay. At this point, it turns around, right? Because dx d phi has gone to 0. Okay. It starts moving in this direction. Okay. Once it starts moving in this direction, it basically crosses over the 2 gm line, 1 over 2 gm line. Right? Because nowhere here it can stop its motion. Is this clear? If initially it was moving in this direction, then of course it keeps on moving in this direction, right? So whatever was the initial condition, right? Whether x was decreasing or increasing, the eventual fate of the system will be that it crosses the 1 over 2 gm line, right? In terms of rho, right? If rho was decreasing to begin with, it keeps decreasing and crosses over the rho equal to 2 gm line. If rho was increasing to begin with, it reaches this turning point and then starts decreasing and
So
crosses.
is it necessary that once reaching the turning point, it will turn? It could also keep on moving forward.
Well, it cannot move forward, because if it moves forward, it becomes this, a function where it becomes negative, right?
Then d phi
So this is not a physical region, right? So if this function was something like this, what you are suggesting could happen, right? It reaches this point and moves forward. But as long as the behavior of the function is like this, we know that it cannot move forward, right? It has to turn back, and that we can actually see by integrating this equation. Okay, that requires a little more effort. This is like a linear zero, right, of this function. So this equation near that point will look like a square root of rho minus rho naught, right? Because the function is vanishing linearly. Okay? When you integrate it, you can easily see that rho actually turns back. Okay? But even without doing that calculation, we know that it cannot go this way, right? So the only thing that we could say is that could it stop here? Okay? And that you can show is not consistent with the equations of motion. Okay? The motion cannot simply stop here. Okay? When we integrate it, you have to, it actually turns back and goes back. Okay? So this situation will describe a particle that comes out or not comes out of the event horizon, whose initial condition is such that it was moving radially outward and then eventually turns back and falls in, or the initial condition is that it was moving radially inwards and it just falls in. Is this okay? So this is a possible motion, but this is not the case we'll be interested in. Okay? Because our eventual interest will be to study bound orbits. Okay, like the motion of planets around the sun. Okay, how much correction general relativity will give us. Okay? So while this is a possible trajectory, this is not what we'll be interested in.
So if 0 d phi is 0,
Yes.
this means rho is not changing with time, right?
Yes, that rho has reached a maximum or a minimum.
So, but it's not necessary that it should go back and.
Yes, the point is, as long as this function is linear, you can solve that equation and you consider it is necessary that it will turn back. Okay, just solve this equation, 0 d phi. Suppose you have 0 d phi.
Okay. Yeah, double derivative can work.
Yeah, I mean, okay. Let's say, is this the correct one? I think this is the correct equation, right?
Yeah.
Yeah. So d rho d phi is like rho minus rho naught to the power half, right?
If we integrate it, this will be some kind
Some
of
constant.
sine.
Okay, near rho equal to rho naught, this is the structure. Okay, rho is starting from say larger than rho naught.
So it is
it's
sine
other-
rho by rho.
It's rho naught minus rho.
Sine by cos.
It's rho naught minus rho because when rho is less than rho naught, this is positive, right? This function. So you just integrate this once. So you'll get rho naught minus rho to the power half C phi plus another constant. Okay, there are probably factors of half that I have missed. Okay, 2 times this. Okay, because it's 0 over rho naught minus rho to the half, right? So you have to integrate it. And this basically says that rho naught minus rho goes as C phi square. Then when we integrate this, attach some constant. Okay, we will solve. And that means that phi equal to minus a over c, where rho has become rho naught. It reaches, but it's a minimum, right? So rho basically reaches, rho minus rho naught reaches a minimum and then goes up. Or it reaches a maximum and goes up. I mean, yeah, so rho is rho naught minus this, yeah. So it reaches the maximum and then goes down. Is this okay? See, by integrating this equation, you can easily see that it just cannot stop here.
See, if that point is, we can establish that point is a unstable equilibrium, then it is.
Yeah, I mean, okay. This is of course, it is an unstable equilibrium. You can see it from here, right? It's a, if you think of this as a one-dimensional dynamical system as a function of rho and phi, it's an unstable equilibrium. So it will, if you deviate a little bit, it will go towards this. Okay. This one is more interesting. Okay, this one is more interesting because this has two pieces, right? One is here. This will again describe a similar motion, right? The particle comes in and then goes back again. But here we have 2 points, x plus and x minus, which is 1 over rho plus, 1 over rho minus. Between these 2 points, this function is positive. So this is again another physical relation. Okay? What does this mean? This means that rho as a function of phi can oscillate between these 2 points. Right? 0 d phi changes sign at these 2 points. Okay, again by the same kind of solution, you can solve the equations near one of these 2 points. Okay. And you can check that d rho d phi, okay, rho either reaches a minimum or a maximum around these points. So d rho d phi changes sign. Okay. So in such cases, rho will start oscillating between x minus and x plus. And that is what we normally think of as the bound motion of a planet around the sun, okay? Or what we normally think of as an orbit, right? Because for an orbit, the distance from the center of attraction, okay, varies, okay, but it varies between 2 definite limits, right? If it's an ellipse, for example, right, the center of attraction is at the focus, the radius reaches a maximum, the distance reaches a maximum and a minimum. Okay? So if you are trying to describe the orbit of a planet around the sun, okay, this is the case that should be studied. Is this okay?
So there can be also a case where this minimum is just this right hand side minimum.
Here, yes.
This curve.
Here.
Yes, this point is just touching the x-axis. That will
No, that will.
also be a case.
Yes, yeah, that will also be a point, exactly. Yeah, that can happen.
Because I was thinking that then if this is the solution, then
Yes.
there is a whole lot of region of rho which is
That is true. Yeah, so that can happen. So that's a very special point. Yeah, that requires adjusting n and k appropriately, and then that has to be studied separately.
but if this is the case, then there's some region of rho which is inaccessible.
Some region of rho which is inaccessible.
Because in that case fx is negative, so that region is not physically.
Here, yeah. Here the point is, if you move in this region, right, you will never get to this region.
Okay.
Right? So that's physically the motion of the planet.
Okay.
Right? The planets don't come arbitrarily close to the center, right? Is this?
In the case of if one point touches the line, in case of we have a coinciding root of the system.
Yeah, so then again you can integrate
So
it and see
this
what.
k and n will be related to this 2gm x directly.
Yeah. Right? Of course, all this x plus x minus etc. are of course determined in terms of these. Right? The coefficients that appears in this equation. Right? Because they are after all roots of that equation, right?
And k,
Of that
n and
curve.
k are the two unknown constants.
Yes,
We have
exactly. N and k are two unknown constants.
So,
N, k and then m also, right?
M.
M is the mass of the center of attraction. Now, of course, I will want us to check afterwards that what are the allowed possibilities, right? Because here, if you are allowed to vary this arbitrarily, then you can get any arbitrary cubic polynomial, right? Then all possibilities have to be allowed. But of course, you know that n is negative, k square is positive, m is positive, right? So not all of these possibilities may actually arise in physical situation,
yes.
right?
But-
But we are not worried about what possibilities can arise. We only want to focus on one possibility, but you want to see what else can happen, right?
Just
Yes.
like if we put the condition he said, like if it touches that point,
Yes.
then there will be two possible trajectories for a particle vector. Because in that case, reaching by through any of the orbits or from the particle moving from infinity
Yes.
reaches that point, doesn't ensure that it will go in or come out.
Well, there is a definite answer. You just have to integrate it and see what you get, right? Not that the answer cannot be found. Right? It's instead of rho minus rho naught to the half, right? You will get rho naught minus rho there. Right? And you can integrate and see what the answer will be. Right? Is it clear? Because a differential equation has to have a solution, right?
Yeah.
Okay, so the solution to a differential equation will tell you whether the particle is going to stop here or whether it will go beyond or not. Right? So the answer is not ambiguous.
So can it be possible that for a certain choice of this n and k,
Yes.
solution may not exist?
No, we'll see. We are considering all the possibilities. Huh? We know already some boundary conditions, right? With that boundary condition, now we are going to list all the possibilities, right? And see if the solution exists or not.
So one thing I'm not clear on is why are we not, why do we not go into the negative region? Why is negative region not a physical region?
Meaning x larger than 2gm. X larger than 1 over 2gm is that?
No,
this
the
region.
negative region, f is negative. Why is the answer?
Because rho is positive. No, rho we are restricting. Oh, why isn't f? Oh, f negative because f sits inside the square root,
Oh,
right?
yeah.
So you cannot make turn it negative. Okay, so let's consider the other case, right? Case 2, which is this.
This for our
Yes, of course, the allowed region depends on various parameters. No? Yeah, the n and k and n, right? So it certainly can vary from planet to planet. It depends on initial condition.
Absolutely doesn't depend on
Okay, so case 2, we have f, what's this x again? So x is 1 over 2 gm.
So qualitatively, these things are similar to the Newtonian gravity.
Pardon?
Qualitatively, these things are, look similar to the Newtonian gravity thing. Is there
Yes.
this kind of new physics coming?
Well, the point is with the in Newtonian gravity you will get two cases. We'll see. I mean, let's get there because in Newtonian gravity, the r equal to 2 gm, that boundary is not really there.
Yes.
Right? So you can follow at the center, that's a very special trajectory. Otherwise, you always can follow it to see what happens for r, even when r has gone beyond 2 gm. Right? That's the difference here. That there is a boundary and we have to study the thing equation separately, independently, differently beyond that. Okay, when you cross, what happens when you cross the r equal to 2 gm line. Okay, so case 2 is where this is positive. It's here. Okay. So now we have a possibility. First possibility is that it just goes like this. That's certainly allowed. So this will say A, and the second possibility will be goes like this.
Twice.
So if we have more than 2 roots, then
Yes.
multiple such pockets are possible.
But upon you have at most 3 roots, right? That is a cubic function, right? So that restricts adding more things here. That's why I mean, even though you are interested in between these 2 points, it's useful to look at the function as a whole. Right? The cubic, because the function is cubic, we know that it cannot have more than 3 roots, right? Irrespective of where it is. Okay, so these are the 2 possibilities, right? This is 1 over 2. So this one, the function never becomes 0,
This is a goal then.
right? So if this exists, if this solution exists, this corresponds to basically a trajectory which either goes up to infinity or starts from infinity and goes all the way into the Schwarzschild radius, beyond the Schwarzschild radius. This one, see this, the f is never 0, right? So rho can never turn around. Rho is either continuously increasing or continuously decreasing.
So x can be negative.
Here,
Sir. In that case, x can be negative x.
no, x is 1 over rho, so rho cannot be negative, right? See, rho is always between 2 gm and infinity, right? So x, this is the physical region, right? Between 0 and 1 over 2 gm.
Means x cannot be negative.
X cannot be negative, no, right? Because x negative means rho negative, right? That doesn't make sense. The physical region is between 0 and 2 gm. Again, I am not at this stage analyzing which of these possibilities could arise for a physical choice of n and k. Okay, we could do that, but let's not worry about that for now. Okay. If this is an allowed possibility, then it will correspond to a particle starting its motion and going all the way to plus infinity, or a particle starting from infinity and coming in, and eventually crossing the 1 over 2 gm line. Is clear? Then x goes all the way like this or all the way like this.
Something like an escape velocity. This reaction is some kind of escape velocity.
Yeah, exactly. This one, the physical regions are here and here. This is similar to this one, right? There is only one turning point. Right? The particle comes in, turns around and falls back. Okay, this is another possibility. What about this one? One turning point.
Actually, turn
right?
and go to infinity back.
So this point x equal to 0 is actually rho equal to infinity. Right? So this will correspond to the motion where the particle comes from infinity and goes back to infinity after turning. Right? The motion of comets around the planet will be like this. Well, not comets are still bound orbit, but you can imagine that they something flies off, hyperbola, right?
Hyperbolic fixed point.
Well, just think in terms of central motion, right? One over r potential. Okay, the particle comes in from infinity and goes off to infinity, right? If the particle has enough energy, it can do that.
It's like parabolic.
Hyperbola.
Yeah,
Parabolic or hyperbolic.
parabola or exactly.
Parabola is the transition one, right?
Yeah, that's the exactly zero energy
Yes, zero energy.
motion. So this will describe motions of that kind. Okay. Again, it's useful to study. Right? If you are going to study the motion of objects around the sun or other planets, but this is not again the kind that we are interested in. No, we are interested only in the kind where we describe motion of planets. Okay. So that basically allows us to zero in on this situation. Okay. This is a situation in which actually describes motion of planets around the sun, around other stars. Is this clear? Okay, so that means of all these possibilities, we choose case 1b, okay, to focus on and study in detail. Doesn't mean that the others don't exist or the others are not interesting, but at least for our purpose, we will focus on this.
So if n plus 1 is equals to 0, then it will be like a bound problem will be infinity.
Yeah, n plus 1 equal to 0 will be like in between, right? So it's here.
That will be like.
There will be a turning point and infinity. So if I throw a
Yeah, that will be
particle-
like a parabola. Yeah.
Yes.
Right? If it starts from here, for example, right, then it's between 0 and this. Right? So that will be the analog of the parabola.
In case a comet is like.
Well, the comet is more like a very elongated ellipse. Right? If it comes back, that means it's a bound orbit. Right?
M equals 0 is for massless particle.
Pardon?
M equals 0 is for massless particle.
Well,
n plus 1 equals to.
n plus 1 means something n plus 1 equal to 0. Right? So n plus 1 equal to 0 means that this is
The parabola.
here. Right? So it's x equal to 0 is the turning point, right? But that of course is at infinity, right? So that basically means that the particle is slowing down as you are going towards
Never
infinity,
turn back,
right? But it actually goes to the velocity goes to 0 only it reaches infinity.
Even then, there can be two kind of possibilities. Like two kind of orbits can be there. One is the straight falling orbit. So
But that's a special case of a parabola.
yes. But
In,
what I'm
in
trying to
central,
say,
normal central motion.
yeah. But what I'm trying to say, in case of this zero analysis, like we are trying to find out zero of this function f. In that case, that it can have a single zero or
Yeah,
three zeros.
straight falling orbit will be like this. I mean, here if it goes like this, right?
Yes.
Then
But-
infinity is like a fixed point. Right?
But if I throw with correct denomination the particle, then it will never come back actually. It can never reach infinity.
I don't
Right?
know.
In that problem.
Infinity from there.
No, it can reach infinity. I mean, if it's here, for example,
Yes. But what I am trying to say, if we throw the particle, in case of
through the particle from inside,
Inside.
throw it radially outside.
radially outside,
You
then
can give it the escape velocity so that it reaches infinity.
yeah, it just reaches infinity, but
Yes.
it doesn't come back.
Yeah, that's the parabola, right?
Yeah.
The parabola reaches infinity and doesn't come back.
So can we look for the light case from here also, case 2 putting n equals to 0?
Yes, n equal to 0, of course, the light case. Yes, so that's a very special case that we have already solved.
Yeah, so it's showing like you have a bounded, no, you won't have a bounded, right?
No, you don't have a bounded motion for light.
Case
So
2 is
case two-
both are
Case to be.
Okay.
N equal to 0. Yeah. N equal to 0, this n plus 1 is here.
1.
sense? So let's now see how to study this. Okay, that's conceptually it's straightforward. You just have to solve the differential equation.
বিশ্বাস না নিয়ে এখান থেকে একদম
So again, the main difference from the Newtonian gravity is that there we could just think of the ellipse and parabola, or the ellipse and hyperbola. Parabola, of course, is just a boundary between the two. Okay. So you either have a bound orbit or an unbound orbit. Right? Those are the two cases. Okay. Radial motion is very special. Here, the reason that there seems to be more cases is because among the bound orbit, some may go beyond 2 gm, r equal to 2 gm, right? Some may enter the r equal to 2 gm radius, okay? And once that happens, that has to be treated differently. Okay? Similarly, in the unbound orbit, okay, in normal Newtonian gravity, unbound orbit can go as close to the origin as you like. Right? You can put a very high velocity particle which goes very close to the origin. Here, again, that has to be treated differently from the one where it goes outside the Schwarzschild radius. Because an orbit that goes past r equal to 2 gm is qualitatively different from the one that goes outside r equal to 2 gm. Okay, that's the reason why there seem to be more cases here. Right? We considered the 4 cases instead of just 2 cases. Is this okay? Okay, for r equal to 2 gm we have to see what happens. Okay, that will come later. Okay, so if we had written in terms of x, let's also write in terms of rho. This was n minus k over rho square and 1 minus 2 gm k square plus 1. So if we know vanishes at rho equal to rho plus and rho minus, because you have already focused on this. Yes. Okay, rho plus and rho minus are the farthest distance and the shortest distance. Then x plus is the smallest possible value of x, right, which means it's the largest possible value of rho. Okay, 1 over x plus, and this is the largest value of x, which means the shortest value of rho. So you already know this, okay, and in using this we can express n and k in terms of rho plus and rho minus, right? So let's see how to do that. We will not use it, but we'll do that anyway. So you have n minus k square over rho plus minus square is equal to minus 1 over 1 minus 2 gm over rho plus minus. So n, okay, suppose you want to calculate, first let's calculate k square. So all you have to do is take this equation for rho plus, take this equation for rho minus and subtract. Right? N will drop out. So you will get k square times 1 over rho plus square minus 1 over rho minus square. This minus n and this minus n cancels. So 1 over 1 minus 2 gm over rho plus minus 1 over 1 minus 2 rho minus. So this gives k. Similarly, to calculate n, what you can do is you can just multiply by rho plus square the first equation and by rho minus square the second equation, and then subtract, because then k square will drop off. So n times rho plus square minus rho minus square will be minus rho plus square over 1 minus 2 rho plus minus rho minus square over yes, is that it? So what I did, I multiplied this equation by top equation by rho plus square. So n rho plus square minus k square is minus rho plus square over this. Then I took the equation for with rho minus multiplied by rho minus square. Then again I get n rho minus square minus k square is minus rho minus square over this, and then I subtracted to remove k square. So this determines n. Okay. So if you are studying the motion of a planet, okay, and if you know the shortest distance and the largest distance from the sun, then that allows you to calculate n and k. Okay. So far there are unknown constants. Okay. Now we are saying that if you know the orbit of the planet, how to calculate n and k. Okay, just measure the shortest and largest distance from the center, and in terms of which you can determine n and k. Okay. So it's clear that those are the only two parameters essentially, right? Rho plus and rho minus, and of course then m is another parameter. Okay, the mass of the attractant. Right, and what is it that we are trying to calculate? Okay, so now I can plot rho versus phi. Phi we know always increases. Okay, by choice of convention, you are taking k to be positive, so phi always increases. Rho is bounded by two values, rho minus and rho plus. So we expect that rho, motion of rho will be something like this. Is this okay? The rho has to keep oscillating between rho minus and rho plus. Right? There is nothing else that it can do. So what we want to calculate is this distance, which I call delta phi.
In a time period.
This is not the time period. This is the amount by which phi changes when rho comes back from maximum to another maximum. Right? If the orbit was periodic,
Then it's 2 pi.
then this is 2 pi.
Yes.
Right? Because that's what you are familiar with in normal orbit, right? But we want to calculate and see if it's really 2 pi or not, right? I mean, from whatever I have said, there is no reason to expect that it is 2 pi.
Yes.
2 pi. So you want to calculate this, and this will determine whether the orbit is periodic or not. Okay? And if it's not periodic, then how much it deviates from periodic orbit. Now to calculate this, is not hard because you have to only integrate the differential equation from rho minus to rho plus, right? Because we have the equation d phi d rho. What was it? This is k times 1 over square root of x, right? And then rho square also. So you have to integrate this equation, but you have to keep in mind that d phi d rho changes sign here and here. Okay, so if you are integrating from here to here, d phi d rho is negative in this region and positive in this region. So you could do that, or by symmetry we know that you can just calculate the period that in that amount by which phi changes from here to here and then multiply by 2. It's the same integral you have to calculate, right? Because you have to only integrate from rho plus to rho minus, right? You either integrate from rho plus to rho minus with a minus sign, or rho minus to rho plus with a plus sign, right? It's the same integral. So delta phi then will be integral twice integral rho minus to rho plus k over rho square 0 or square root of 1 minus k square rho square 1 minus k rho plus 1. Okay, so this is the expression that we have to calculate, and everything is known here because after all k we have determined in terms of rho plus and rho minus, n we have determined in terms of rho plus and rho minus. Right? So if you want to calculate it exactly and you don't know how to do it, you can just put it on a computer and calculate it. But we will try to evaluate it approximately and see how much it deviates from 2 pi. Okay? Because we expect that at least in Newtonian limit it should give us back the answer 2 pi. Okay? Because there we know the orbits are periodic. Okay, so you want to see how much it deviates from 2 pi by taking into account the first correction due to general relativity.
If you try to look at the metric, then the GR effect is coming from the fact that the psi and chi is not 1, right?
Well, that's not true because psi and chi was 1, there will be a flat space time.
Yeah, so
Then there's no gravity at all. See, GR effect is coming because psi and chi, you have to take into account the 2 gm over r part of psi and chi because G is 0, 0.
yeah, that's what I'm trying to say, that 2 gm over rho.
It's not fully GR. Part of it is Newtonian gravity, right?
Yes. Yes.
So you cannot
Yes,
just take 2
yes.
gm over rho equal to 0 and get GR.
Yes.
Get Newtonian
You
gravity.
can expand the psi and
Yes.
take the
Yeah, so you have to expand
first
it
order term.
and keep the first order term.
Because this G00 is itself the Newtonian potential.
Exactly, G is part of G. Yeah, so what you are suggesting is that if we just set gm by rho equal to 0 in psi and chi, then that is a Newtonian limit. But that's not true. That's flat space time, right? In that space time, there will be no effect of gravity at all, right? Even the Newtonian gravity you will not see. So you have to expand appropriately and keep the first non-leading term, right? And we will organize it in such a way that we don't have to keep more than the first sub-leading term, right? We will organize this calculation so that the first correction itself is clear. Okay, but you cannot just at this stage take 2 gm and set it equal to 0 and say that's the first correction. Okay, so we change variables. Okay, that's the first thing we should do. X is 1 over rho because clearly that's easier to use. So this delta phi then becomes 2 integral. There are two effects. One is that the dx is minus 0 over rho square, but this you will also change the limits of integral because x plus is less than x minus, so x plus to x minus now t times dx inverse square root of fx. Okay. And now let me write fx again because what we are using is fx is n minus k square x square times 1 minus 2g x plus 1. Now we already know something about fx because fx equal to 0
At x plus and x
is at x plus and x minus, right? So you already know that fx, two of the roots of fx are x plus and x minus. So fx should have a term like x minus x plus.
times x.
Let me write this as x minus minus x because after all x
Positive.
lies between x minus and x plus, right? So I'm just using positive factors.
And times factor. over.
So times the factor. So what is the most general structure of the factor?
X minus some constant.
X minus some constant. X minus some constant, but there is also an overall constant, right? Left of x.
Yes.
Is this clear?
Hmm.
I have factored out two of the roots.
But there
It's a cubic polynomial, so it has at most three roots, right? So once I factor out two roots, okay, only one root remains, right? Let's call that a. So it's x minus a, and it can also be multiplied by an overall constant which I am calling c. Is this okay? Right? The goal is to determine c and a by looking at this.
So we took x minus x, what was the
X minus?
x minus minus x instead of
Oh, because x lies between x plus and x minus, right? So I just wanted to make both of them positive. I could have written it as x minus x plus, x minus x minus, but that basically will change the sign of c. So how do we determine c and a?
you just multiply this expression and compare with that.
So that's one way, but that is it's even simpler. We have to just look at various limits.
Yes.
As x goes to infinity, how does it go? This expression. Minus x cube, c times x cube, minus c x cube, right? Plus higher, lower order terms. Right? X minus x and minus x square and x minus x cube. What about this?
This k square 2gm.
So this is k square 2gm times x cube, right? So this
Minus
should
c is
be
equal to
k square times 2gm x cube plus. So that tells us c. C is minus 2k square 2gm k square or minus k square plus 2gm. Is this okay? A. What is the easiest way to determine A? You know a formula for the sum of the roots. If you have a cubic equation,
yes.
what is the sum of the roots?
Sum of the coefficient of
Coefficient of the x square term. Sum of the roots is the coefficient of the x square term, but you have to normalize the x cube term to 1. Right? Then the coefficient of x square term gives you negative of the sum of the roots. Right? Okay. So let's look at we already know that this is the leading term is this, so we have to calculate the order x square term. So what is the order x square term here?
K minus k.
Minus k square x square, right? Because this is linear. Plus term. So if you take out the factor of 2gm k square, then you get min x cube minus 1 over 2 gm x square plus etc.
This will be x plus x minus.
Yeah. So x plus x minus plus a should be 1 over 2 gm. So a then is given by 1 over 2 gm minus x plus minus x minus. Okay, so in this field, now try to calculate this integral. Okay. Remember that so far you have not made any approximation. Right? Whatever you have done is exact. Right? Because the fact that this is a product of three terms, there is an approximation involved in this. Right? And you just determine the coefficient by comparison. Yes.
Can we then explain why you have multiplied this by 2 delta phi? So
Because it goes, I have integrated only from rho minus to rho plus.
yeah, but phi and considering it to be split, it can multiply.
Yeah, it follows from the equation. This equation is valid universal, right? Okay. So if you integrate from rho plus to rho minus with a minus sign, that's what you have to do, right? What you have to add, if you don't include the 2, right? What you have to include is the integral of rho plus to rho minus. We are going from here to here, same integral, but with a minus sign. You have to pick up negative square root because rho is d rho d phi is negative here, right? That's exactly equal to integral rho minus to rho plus of with a positive integral. Is that okay? Right? So minus, so it will be this minus integral rho plus to rho minus of minus of this. Sorry, minus integral rho plus to rho minus of this. You just change the limits of integration, and that becomes plus of the same thing. Is this okay? Okay, so let's proceed with the calculation. So delta phi will be 2k times integral x plus 2x minus dx over from fx. First I take out this part k times square root of 2gm and then inside the square root I write x minus x plus x minus x, and because of this minus sign I have to write it as a minus x, okay, not x minus x, a minus x. So
There
that's
was
a
a
minus x.
K, right? There was a K, right? This K will cancel it.
There is this k,
Yeah, we'll cancel with another K.
this k,
Yeah. Okay. You will.
there is a k,
Okay.
k to begin with, and inside c this is k times square root of 2gm. We cancel this. So let's write this as 2 integral x plus 2x minus dx plus 2 of x minus x plus x minus x. Okay, we'll just write this separately. The reason will come here. Now I have a minus x, right? I'll put this 2gm factor with a minus x. Okay, so 2gm times a minus 2gm x. So 1 minus 2gm x plus x minus plus x. It's the same thing written slightly differently.
Can you repeat? Sir,
Yes.
can you repeat that one?
Yes. So x minus x plus x minus minus x is here, right? So we have only a minus x. A is given here. So a minus x is 1 over 2gm minus x plus x minus plus x, right? Now I just take the square root of 2gm and multiply it. A minus x, right? That gets rid of this 1 over 2gm. This becomes 1 minus 2gm times this. The reason that I am writing it this way is because this part is in fact the Newtonian part. Okay, if you had done Newtonian gravity, you will get just this part. Okay, so this is the correction. Okay, but we will see as we go along. Okay, after you do some scaling, it will become clear that this is indeed the correction.
So
Yes.
you're saying that that is the Newtonian part, that will give 2 pi.
Yes, this will give 2 pi. Okay, it still doesn't look like it will give 2 pi, but it's actually a simple integral. Right? So you basically have to make some change of variables and remove this x plus x minus from the problem. See, now we have inside the square root, it's a quadratic function of x, right? So you have to basically write it as a complete square. Right? The standard way we do these integrals. So x minus x plus times x minus minus x is minus x square plus x minus minus x plus x plus minus x plus x minus. So this I can write.
So x minus plus x. Second term.
Yes, x minus x. So this one I can write as x minus plus x plus over 2 minus x whole square. Or it doesn't matter, I can write this one also, x minus this whole square, but overall with a minus sign, plus x minus minus x plus. So when you expand this out, you get minus x square, right? The cross term gives you x times x minus plus x plus. Then you have the square of this. That square combines with this square to give you minus x plus x minus. So this now suggests what variable change you should make, right? So y should be x minus plus x plus over 2. So this becomes minus y square plus this thing square. Okay, but then we want to scale. V should be y over x minus minus x plus over 2. With the change of variable, this becomes minus x plus square by 2 whole square times 1 minus b square. Okay, because this is minus y square plus this. Okay, I have scaled out these factors, so these times 1 minus b square. Dx is dy, which is dv over x minus x plus over 2. Sorry, dv times this. And this x plus x minus plus x, this becomes x plus x minus plus x is y plus y. So that's 3 half x plus x minus plus half x minus y. Limits are easy to figure out. When x is equal to x plus, y is minus of x plus minus x minus by 2. That's v equal to minus 1. And the upper limit is v equal to plus 1. So delta phi will be 2 times minus 1 to 1. Okay. So dx, after all this, you see that there is a dv times x minus x plus by 2. But that basically cancels this factor that comes from the denominator, x plus minus x plus by 2. So it's just dv over square root of 1 minus b square. 1 minus, that is a 3 half, so minus 3 gm x plus x minus minus gm x minus x plus v to the power minus half. So now that we have scaled out everything, now let's see what we can, as a small, you see x plus and x minus are 1 over rho plus and 1 over rho minus, right? So you know that 2 gm over rho is small for planetary distances, right? And rho is lying between rho plus and rho minus. Okay? So assuming that even at the closest approach 2 gm over rho is small, we can use an approximation that this quantity is small, right? Because 3 gm times 1 over rho plus 1 over rho minus. Similarly here, gm times 1 over rho minus 1 over rho plus, right? Again, as long as gm over rho is small enough, okay, even for rho equal to rho minus, you can take this to be small. V of course lies between -1 and 1, right? So that doesn't change this fact. So you can now expand this out in a Taylor series expansion. Okay, because this quantity is really small, right? Compared to the leading term, which is 1. So we can expand it out and we get 1 plus 3 half gm times x plus x minus plus half gm x minus x plus times t plus higher order terms. And now you see that this contribution vanishes. The one that is linear in V, because V goes to minus V symmetry. Right? V runs from minus 1 to 1, so this will basically cancel out. Okay. So what we get is 2 times 1 plus 3 half gm. And now let me write in terms of rho, 1 over rho minus, and this integral minus 1 to 1 dv over square root of 1 minus v square, and this is essentially pi. Okay, you can just change variables from v to cos theta and you get it for pi. So the answer that then is is 2 pi plus 3 gm so pi, yes, 3 pi. So you see that indeed it's not periodic, right? The axis keeps rotating. Okay, so what will it look like? Okay, it's very small, of course. Okay, so in one revolution you may not even see it. Okay, so it will be like this. So in Newtonian gravity, it will happen in ellipse. Right? Now it will be almost an ellipse, except that it will move a little bit away. From being an ellipse. I'm not drawing it properly, but you can see what happens. Right? The ellipse, the axis of the ellipse will keep shifting. Right? Because if you define the axis of the ellipse by saying at which angle, okay, the distance becomes minimum or maximum. Imagine that which angle the distance becomes maximum. Okay. Then that angle will keep shifting. Right? Because after it becomes minimum not after a 2 pi rotation but a 2 pi plus something rotation. Right? So it will look like the axis is shifting. Okay. So if you observe it over a large number of oscillations, okay, you will see that the axis actually has tilted and gone to some other position. Okay. And you can also calculate after how many revolutions it will again, the axis will again come back to its original position. Right? That's basically 2 pi over this. Right? Each revolution changes its angle by this much. So after 2 pi over this many revolutions, okay, the axis will again come back to this original position. So this again is one of the tests of general relativity. Okay. The axis of Mercury is known to physicists, okay, and large part of it is due to other planetary effects. Okay. But it was known that even after taking into account all the effects of the other planets, okay, it was not, the Newtonian gravity was not able to explain the exact amount of precision that the orbit was going through. And once you took into account the general relativistic effects, okay, the result agreed with what was observed. Okay, so this was one of the early successes of general relativity, okay, explaining why the orbit of Mercury precedes.
Is this a closed orbit?
Pardon?
Closed orbit.
No, it's not closed, right?
It's not closed.
Because, well, the point is if this was, if 2 pi over this was an integer, you could say after an integer amount of revolution it will exactly come back to the original orbit, but there is no reason why it should be an integer. Right? So it's not really a closed orbit.
But we can see it to be a by b kind of a form, so it's a rational form, right?
Well, it need not be rational, no? I mean, these are not integers.
But we can always write it in a by b form.
But a and b are not rational, not integers.
In
any number can be
in principle, g and m can be rational.
Well, in principle it can, but it never is. So, I mean, a generic number if you pick is
Yeah.
never rational.
Rho
Right?
and rho plus
So unless there is reason for it to be rational, okay, for any real number, right? I mean, rho plus rho minus g and m, it will not be a rational number.
But divide by 2 pi is also.
Yeah, well, pi cancels.
Pi
right?
cancels.
So that's what you would think, but that doesn't help because I mean the fundamental constants, right? I mean ratios of fundamental constants or the physical distances measured in fundamental constants are not generically rational, right? So there is no reason why the orbit should be closed. Okay, of course you can look for special rho plus and rho minus for which it will be closed, right? For which this
If gm,
is
rho
rational.
plus and rho minus are rational, then the orbit will be
See,
closed.
okay, of course, GM is dimension full, so there is no question of that being rational. It's this combination,
Yes.
okay, which is a dimensionless number. Right? That you could ask whether it's rational or not. If it happens to be rational, then the orbit will be closed, but otherwise not.
No, actually, what I'm trying to actually argue that this is already a by b kind of a form, right?
But they are not
No, but A
integers.
and B are not integers or rational numbers. A by B doesn't help. No, I mean it has to be A by B with A and B integers.
Yes. So if a is rational by a b is rational, then the
But these are, see, G and M are dimension full numbers. So it doesn't make sense to say G and M are rational.
Yes.
Right? It's this ratio
Mhm.
which is dimensionless.
Hmm.
Right? That you can in principle ask whether it's rational or not. There is no reason for it to be rational, but it's a dimensionless number. Right?
Yes.
It makes sense to ask whether it's rational or not.
For a dimensionful number, it's not a
Exactly.
good
Then
question.
it
to
depends on
ask.
what unit you use.
Yeah, if in a rational unit it can be a rational number, so that's a very
Exactly.
complicated.
Okay, so I think maybe I'll stop here. So tomorrow I'll start discussing what happens beyond the R equal to 2gm. Yes. Okay, because that's really special for the partial solution. Okay. So far what we have done is just minor corrections for Newtonian gravity. Right? It's not a drastic departure from what we already know in Newtonian gravity. But we'll see that once you start asking what happens at rho equal to 2gm, okay, we'll really go far beyond what we expect in Newtonian gravity. Yes.
So when we use these graphs to get the solution, then we assume that our solution is valid up to 1 over 2g.
Yes, and we don't know what happens beyond 2gm.
But in case of sound, the short cell radius, where it is less than the physical radius of a star.
Yes.
For that case, it will be beyond.
No, in that case, if the Schwarzschild radius is smaller, then of course you have to assume that the distances that you are talking about are larger than the physical radius. Okay? Because we are using the metric, the Schwarzschild metric, right? The metric itself will not be valid if the planet enters the surface of the star, right?
So means these points, these are well away from the physical radius as well.
Exactly.
Is there
That's
a way
right.
to assure that, or it is observed?
No, it's like Mercury planet. I mean, it's certainly outside the sun, right?
But not much further.
Not much farther, but still large compared to the radius of the sun. I mean, it doesn't enter the sun, right? So in that sense, I mean, you already know that it's outside the physical radius. Okay. But there are other Newtonian connections, right? Because there are other planets which are affecting the motion of the Mercury, right? And also other planets. So all of those effects have to be taken into account, right? All standard Newtonian connections have to be taken into account. And only after that, right, you can ask whether it agrees with the Newtonian prediction or not. Right? And so what people have found is that even after you have taken into account all of the corrections, right, it didn't agree with what you expect, measure experiment.